Hello good people, I'm going to continue talking about hybrid orbitals. Previously I looked at the sp3 hybrid orbitals of alkanes. Now I want to explore the hybrid orbitals of alkenes and alkynes. To that end, let me bring in ethene. Recall that ethene has two carbons that are linked by a double bond. In order to explore the hybrid orbitals, I'm going to focus on the carbon on the left. Let's call that carbon number 1. Here is the energy diagram for the orbitals of carbon number 1. Note that now we have 3 sp2 hybrid orbitals. And we also have one remaining 2p orbital. What do these orbitals look like? Let me start with the axes and the 1s orbital in the middle. Here are the 3 sp2 hybrid orbitals. Note that they are 120 degrees apart. This matches the distance between the angles of ethene. Here is the pz orbital. Due to my amazing artistic skills, there are a couple of things that are not clear on my little drawing. The sp2 orbitals are all in a single plane, and the remaining pz orbital is perpendicular to that plane. This means that while the sp2 orbitals are 120 degrees apart, the pz is only 90 degrees apart from the sp2 orbitals. What about the valence electrons? Well, here they are in black. Notice that carbon 1 has 4 unpaired valence electrons. 3 of them are in the sp2 orbitals and 1 of them is in the pz orbital. Carbon 1 is bonded to 2 hydrogens, so here they are, the fuzzy red spheres, and I have also added those hydrogen electrons into the sp2 orbitals. To demonstrate the next part, I need to bring in carbon 2. It also has 3 sp2 orbitals and a pz orbital. I have already added the hydrogens that are bonded to carbon number 2. And now I'm going to drag carbon number 2 closer to carbon number 1 so that the sp2 orbitals of carbon 1 and carbon 2 overlap. By overlapping these two sp2 orbitals, we have created a single bond. Whenever we overlap two orbitals head-on, we talk about a sigma bond. This little symbol that looks like an upturned number 6 is the lowercase Greek letter sigma. How does this sharing of electrons, this overlap of sp2 orbitals, look on my orbital energy diagram? Well, I can add another electron here. What about the electrons in the pz orbitals? How do they overlap? Well, they do not exactly overlap. Instead, they form a bridge. And we could represent it something like this. This bridge between two pi orbitals on two different atoms is known as a pi bond. A common misconception that may arise from this drawing is to think that we have created two pi bonds, because it seems as though we have two bridges. True, but these two bridges constitute a single pi bond. And to make the language a bit more frustrating, now we have a sigma bond and a pi bond together, which result in a double bond that we see over here on the left. An important thing to note is that we can rotate around a sigma bond, but we cannot rotate around a pi bond. Because if we were to start to rotate either one of these carbons, the bridge would collapse. The pi orbitals would no longer align. The fact that we cannot rotate around a pi bond gives rise to certain types of stereoisomers. More on those later too. For the sake of completeness, let me indicate the sharing of the p orbital electrons on the energy diagram as well. Alright, so this is what happens when we have a double bond. What about a triple bond? Here is ethyne. We have two carbons. I'm going to label them carbon 1 and 2. Note that the bonds are 180 degrees apart. What does the energy diagram of one of these carbons look like? Now we have two sp hybrid orbitals. And we also have two p orbitals, y and z. As before, we have 4 unpaired electrons, which means we can create 4 bonds. What do the orbitals look like? Here are the axes again. Here are the two sp hybrid orbitals. Note that they are 180 degrees apart. And now we have two p orbitals, py and pz. Here are the valence electrons. One of the sp2 orbitals will overlap with the s orbital of hydrogen. And here it is, the fuzzy red sphere. We have 2 electrons, and therefore we have a covalent bond between carbon and hydrogen. Let me bring in the second carbon. One of its sp orbitals also overlaps with the 1s orbital of a hydrogen. Let me create a sigma bond between the 2 carbons. So I'm going to drag carbon number 2 and place it over here so that the 2 sp orbitals overlap. And I can indicate this pair of electrons over here on the energy orbital diagram by adding another electron in the sp orbital. What is going to happen to the electrons in the py and pz orbitals? Well, now we will have 2 pi bonds. The py orbitals are nicely aligned for a bridge to form, and here it is. And the pz orbitals are also nicely aligned to form another bridge. So in case of a triple bond, we could say that we have a sigma bond and 2 pi bonds. Recall that we cannot rotate around pi bonds. This means that double bonds and triple bonds are more rigid than single bonds. For the sake of completeness, let me indicate the sharing of the p orbital electrons on the energy diagram as well. I can hear many voices cursing my name. That is all for now, and I will see you on the flip side.